Okay, so let's start. So I'm continuing what I was talking about with the CGHS black holes. And here is a picture on the left hand side, which is the CGHS black hole up here that I was talking about. And so what we saw is that if you include the um, the, the semi-classical correction, then this that singularity which is tamed up here does not reach cry plus, but ends at finite time up here. And then we got this matter collapsing. So matter collapsing up here, and it actually there's a dynamical horizon that joins on, and it becomes like that. And this somehow got doesn't matter. This I don't know why, but this got shifted. Maybe I can maybe I'll make it worse. Yeah, that's better. Good. So this is a picture that we got, and then now I'm going to talk about the spherical collapse in general relativity. Remember, the difference between these two is not that profound, but it is physically quite profound. Technically, it makes it sorry. Technically, it's quite profound because it is you can solve for the matter field without solving for the gravitational field up here, and here everything is coupled altogether. So the expectation here is the following: that the two things are very similar, and therefore we can take over the expectation. So the expectation here is the following: that we got here the dynamical horizon which forms, which is completely analogous to the dynamical horizon, which this is also not correct. Just 1 second. Okay, I'll not worry about it. It got somehow moved. I don't know why. So you got dynamical horizon which is fall up here, and it becomes again time-like, just like this one became time-like up here. And then, but here it will be cutting off before you hit the singularity, and so this part of space-time is a semi-classical space-time. And similarly, here this part of space-time is a semi-classical space-time that I'm looking at. Okay. So recall that to incorporate back reaction of the Hawking radiation, we proceed in 2 steps. In CGHS model, there is a spherical collapse, but with simplification, which make it exactly soluble classically, because one can first solve for matter and then for the gravitational fields. In the scalar field collapse in general relativity, the structure is very similar to CGHS, but now one has to solve for matter and gravity together as a coupled system, and so the equations are much more complicated. But again, I got a trapped region up here, and I got a trapped region here, which is shown in yellow. The CGHS spacetime does not admit an event horizon because cry plus is incomplete here. One can show it explicitly, and semi-classical metric is smooth across across the last rays. Now, from here, where in this case, in the 4-dimensional case, we don't have such a nice thing, because the only way that we have, the only handle we have a stress energy tensor, expectation variable stress energy tensor, is all numerical, and it really is really just close to the horizon. There are technical limitations for which we cannot take this over, but one expects the same situation as in CGHS in this realistic model. So, but there is an apparent paradox associated with entanglement already in the semi-classical approximation, and this Carlo alluded to this yesterday quite a bit. So, but let me say that in CGHS the same paradox arises, and the resolution that we are proposing in this case really comes from what we have seen in the CGHS model. So, consider first of all, as I did before, a phase in which a 1 solar mass black hole shrinks to the lunar mass, which is about 10 to the minus 7 times the solar mass. In the process is well described by semi-classical gravity. The process here takes 10 to the 67 years. In my papers, I already said about 10 to the 64 years many times, but there is a numerical factor of 1,000 that comes from the factors of pi's and such things that I had missed, so it is really 10 to the 67 years. And so during this period, so during this period up here, we got Hawking pairs going in and out up here like that. So about 10 to the 75 Hawking quanta are emitted. Now, how does one get back up the envelope calculation like that? We have got a black body radiation, so we can look at the intensity, and then from looking at the intensity, we can look at how many photons went out, at what frequency, and we can integrate those number of photons, and that is what gives us 10 to the 75. So, a huge number of quanta which are gone out and corresponding quanta which are fallen in. So, there are correlations between what is happening up here and what is happening out there. The process should be well described semi-classically nonetheless. But now the apparent information paradox is the following. The lunar mass black hole at the end of the evaporation up here, not at the end of the semi-classical, or at this region that I have cut up here, this region up here, we have got a lunar mass at horizon which is only about a millimeter, right, a 0.1 millimeter. And usual people think of this 0.1 millimeter as being a sphere in Minkowski space, and saying that, well, if 0.1 millimeter, how can a sphere of 0.1 millimeter radius contain so many states, right? I mean, even if you say allow the maximum possible wavelength, which is 0.1 millimeter, and you want to know if you have 10 to the 75 such photons, how much mass it would be, it is vastly more than, sorry, say it again, let me start from. How can you have so many quanta? That's what you want to know. So if you say I got 0.1 millimeter 10 to the 75 quanta, then the mass that will have is much more than the lunar mass that I have left over with. And so therefore, the statement is 10 to the 22 times the lunar mass. And so the question is, how can you have so many quanta sitting in this little thing? But as I saw earlier, and we saw Carlo's lecture today, that this picture of the sphere having this geometry inside, like comes from Minkowski intuition, is completely wrong. What we have rather is this extremely long, thin, long stretched tubes up here. End is 0.1 millimeter up here. If you go to the other end up here, you can calculate it explicitly, as I'll see in a minute. Then that other end is larger, as we'll see in a minute. But in between, it is really absolutely huge. The length is absolutely huge, and that is about 10 to the 62 or 10 to the 64 light years. There are delicate things that I think Carlo did not cover, so let me just say a few of those things in detail up here. So so that is going to be the point, that namely that these things are extremely long up here. That is what we want to say. I want to say. But there is a possible resolution of this paradox, which was proposed by Haber and other people, saying that, well, look, there is no paradox, because all these quanta which are here, they can easily come out, because this is really time-like. It's not an event horizon, so they could just have come out continuously up here. There is no problem. But this is not borne out, because you can look at the detailed calculations and you can see that, in fact, there is only inward flux. There is no outward flux here at all. And therefore, this is not really borne out at all, that even though it is time-like, it's tempting. And so I just want to tell you that everybody, me included, the first reaction was, okay, it's time-like. Now, therefore, information can just come out. But the detailed equations show it cannot. And therefore, you should not take just space-time. I mean, you should use space-time diagrams to have some intuition, but they have to be checked by the detailed calculations to say, is this possible or is this not possible? And this is not really possible. So one might think that that the quanta would continuously leak out, but that is not what is happening, and that is the equations show that is not what is happening. Now, so what is the resolution? That resolution is that calculation of the stress-energy tensor in the Schwarzschild spacetime confirm the idea that in semi-classical gravity, there is a negative energy flux across the time-like dynamical horizon, such that there should have been time-like, there is no M here. So that the area of the time-like dynamical horizon would increase, would decrease according to the standard Hawking formula. So the mass of the time-like horizon would decrease, namely mass of the time-like horizon by dV is h bar by this squared. This is the Hawking formula. This comes from this luminosity calculation that Carlo referred to yesterday. And indeed, this is the basis of the standard view that the evaporation time goes like mq. Now, one can argue that in the phase of in that phase of evaporation under consideration, the form of the space-time metric is bounded that is bounded by this dynamical horizons. This form of the space-time metric in this region. I got negative energy flux coming in up here. That can be well approximated by just a white diametric. So the white diametric is like a Schwarzschild metric, except that m is a function of time. Here, whenever I say time, I mean this retarded time, this time of here, v equal to constant is this retarded time. Okay, so ds squared is equal to 1 minus 2 m of v of r dv squared plus 2 plus this. So the only thing that is changed is m is changed here in the retarded times, Eddington-Finkelstein retarded coordinates. The only thing it changed is that m is now a function of volume up here. M is now a function of volume up here. So m along this light ray is larger than m along this light ray. This is later v, if you like. This is an earlier v. At this v, m is just solar mass. At this v, it could be half the solar mass, and at this v, it is very close to the lunar mass. Okay, so that's how the metric looks like. And now, this is because during this phase of quantum corrections of the Schwarzschild metric of classical general relativity are very small, and we are looking at semi-classical gravity. In particular, analogous conclusion is borne out in detail in the semi-classical analysis of the analogous calculation is borne out in detail in the semi-classical analysis of evaporation of CGH's black hole. So let us work with the metric, with this metric, and understand the nature of the space-time geometry it bestows on the trapped region. It is convenient to foliate it, as Carlo explained yesterday. You cannot ask for a volume. I have to give a space-like surface up here. So it is convenient to foliate it with some surfaces, and Carlo referred to the surfaces, which are also used later. Carlo referred to the Schwarzschild black hole, for which these surfaces are fine. They were a trace of extrinsic curvature equal to constant. You know, these are the maximal surfaces that you are looking at. And then these were used by Christodoulou and De Lorenzo, also in the similar dynamical white type of metric up here. But what happens is that in a white type metric, those surfaces do not foliate the entire region. They foliate only the bottom part of this region. They all pile up somewhere here, and they do not really foliate the entire region. But Amos Ori and I found that there are two surfaces that you can consider. One is a naive surface, which is that the radius of the two spheres equal to constant. So space-like surface is such that radius of the two sphere remains constant. I can just draw a space-like surface up here such that the radius here was equal to, say, 1.5 kilometers, then radius up here remains 1.5 kilometers. Or I can calculate the curvature scalar. There's a spherical geometry, there's a nice curvature scalar. There's a most convenient curvature scalar, which is called the Kretschmann scalar, which is just the Riemann tensor squared. Which is just the Riemann tensor squared, and I can calculate that, and it is just given by this. This is a bit surprising, by the way, that all that happens is that m in the Schwarzschild Kretschmann scalar is just replaced by m of v. There are no additional terms like m dot or something like that. That's a very interesting fact up here. So this is a curvature scalar, and so we can look at leaves from here on which the Kretschmann scalar is constant, which are different. In the Schwarzschild case, they all agree, but in the two agree. R equal to constant is the same as here, but in this case, they don't agree. And as I said, the third natural foliation, trace k equal to constant, is not viable with a time-changing mass. I don't know, again, this is shifted. So this is not available because of the because it does not foliate the entire region. If we were to ignore the quantum radiation, the m of v would be just a constant, and the two foliations will coincide, but now they don't. Okay. Let us set v equal to 0 at the start of the evaporation time up here. At the start of the evaporation time, v equal to 0, and see what happens as v increases at the other end up here. So on each leaf, the foliation has topology S2 cross R, and we can calculate the radius of the two spheres as well as the length of the leaf using the metric. And at v equal to v naught, the radius is constant, 10 to the minus 2 centimeters, because v equal to v naught is the place where I got. So I started v equal to 0 up here. I started v equal to 0 up here, and v equal to v naught is where the mass became 0.1 millimeter, became the lunar mass. So therefore, it's 10 to the 0.1 millimeters. So it's 10 to the minus 2 centimeters up here. And then this will be the foliation. The last leaf would have, the last leaf up here would have 0.2, 10 to the minus 2 centimeter radius everywhere. Whereas in the Kretschmann scalar, the radius actually changes. It's not very important, but it changes starting from 10 to the, it increases to 10 to the 5 centimeters, a kilometer, as we move from right to left. But these are differences, but they are minor compared to the fact that in the r direction, the stretching that occurs up here. So what I'm saying is that the tube does not have the same radius in the Kretschmann case. The tube actually, the radius increases slightly, but the length is absolutely huge in both cases, 10 to the 62 light years and 10 to the 64 light years respectively. So this expansion of length is analogous to a cosmological expansion, during which the modes of perturbations are stretched continuously, but now they are stretched from 3 kilometers to 10 to the 62 light years. And during this, so this is for the first one, or 64 for the second one. During this very long semiclassical phase, the partner modes that fell into the dynamical horizon become infrared, and hence there is no obstruction to house the 10 to the 75 quanta partner modes on the v equal to v naught surface, whose mouth has the radius only 1.1 kilometer, the 0.1 millimeter. These modes will have much less mass than the lunar mass. What we know about the renormalized stretch intensity in the Kruskal interior is compatible with this expectation, and this is some of the work that was done more recently with Del Rio and Schneider, and it should be possible to develop this mechanism in great detail. So this is the second part, end of second part, and now it's the singularity resolution, which is the third part. There are three parts. One is quasi-local horizons, the second part is semiclassical region, and the third part is singularity resolution. So only this part of the Kruskal spacetime is directly relevant for singularity resolution. And as I discussed before, it is isometric to the spatially homogeneous Kantowski-Sachs models, where R changes like that, Schwarzschild R, now plays the role of time. And the Killing vector field, which is d by dt, is space-like, and therefore it is now space-like. So it is convenient to change the notation and call R tau, because this is like time, which is changing up here, and what is t in the Schwarzschild coordinate x, because it is space-like. So d by dx is now the Killing vector field, which here is time-like. So here it is d by dt, if you like, little t, and that I'm going to be talking about as d by dx. Then the Schwarzschild metric up here looks like d tau squared upon 1 minus 2 times, 2 tau upon minus 1, plus the space and time part become interchanged, because 2m is now is greater than tau. So therefore, and then the homogeneous slices up here that we got, the metric on them becomes like that. Okay. Now, in the LQG phase space that Christina must have developed in great detail, we got the variables are the connection and the triad, or the density weighted triad. And since in this case we have got only 2 degrees of freedom spatially, because spatially homogeneous. So if I know something at one point, I know it everywhere. And furthermore, here I got a 2 sphere. So I got only 2 components to the connection, C and B, corresponding to the to the two sphere component because it's homogeneous, the same, and also correspond to the r direction up here. And the corresponding momentum variables are going to be p and pc, p and pc. Now, if I do the phase space formulation that Christina must have done, then the thing is that you have a symplectic structure, and you have to make sure that the symplectic structure is actually you have to make sure that the symplectic structure is actually you have to make sure that the symplectic structure is actually well defined, but this volume up here is infinite. This volume up here is infinite because this length up here is infinite up here. So what one does is to just put an infrared cutoff, take a box of length L naught up here, and you will see this much more hopefully tomorrow in Param's talks. And just does calculations in this box. This is like in loop quantum cosmology. This is what one does, put a calculation in a box up here. And at the end of the whole thing, you want to take the limit L goes to infinity. And of course, your physical observables should not depend on this L naught up here. The horizon corresponds to these values, and PC corresponds to 4m squared, and PB at the horizon is equal to 0. Singularity, both B and C vanish, and P and B, PB and PC both vanish up here. So from the singularity, since the singularity is a big crunch type cosmological space-like singularity, one can mimic the ideas from loop quantum cosmology that will be done with Param's lecture today, tomorrow. The key point from Christina's lecture is that the holonomies, namely the Wilson loops of the connection, are a well-defined operator. The connection itself is not. The curvature operator is replaced by calculating the holonomy around a closed loop, dividing by its area, and taking the limit as area shrinks to the area gap. I already mentioned it. I'm repeating it now much more precisely. The minimum eigenvalue of non-zero eigenvalue of area operator is this delta, the area gap. In LQC, two schemes were considered. It's called mu naught scheme, and which refers to the area in the Friedman, Lemaitre, Robertson, Walker coordinates, and mu bar scheme, which refers to the physical area in the quantum state under consideration. And then the curvature operator here, if you look at the holonomy and so on, first of all, the connection only has C and B at the horizon, and then C and B up here. And then it turns out that the curvature operator that you have in the sorry, I'm talking about now LQC for a minute up here. This is loop quantum cosmology, not the Schwarzschild diagram. In which case you only have connection as only one component, which is going to be C up here. And the curvature is now expressible as a trigonometric function of C. And what appears in front is this mu bar, and this mu bar comes from the area gap that I've told you about. And that is really is basically the loop that we're talking about. Its area, its length should be equal to mu naught times this mu or either mu naught or mu bar times L naught. L naught is the fiducial is the length of the fiducial length that I have introduced in my cell up here. In the classical limit, delta and mu bar they both go to 0, and the curvature diverges in the classical limit up here. But quantum mechanics, and that is because C squared diverges. The connection itself diverges, curvature diverges, everything diverges. But here we have got a trigonometric function, and because of that, you have got finiteness. And this is sometimes called polymerization, but this is something that is rigorously obtained using these holonomic considerations. So the bottom line is just that the curvature operator now is regularized in loop quantum gravity, or becomes nicer in loop quantum gravity, and is in fact bounded. It's also non-local at the Planck scale. Using this loop quantum gravity curvature operator in the quantum Hamiltonian constraint, the connection variable, one finds that the quantum evolution does not break down. The Big Bang is replaced by Big Bounce. So this is a loop quantum cosmology detour. The singularity is replaced by a regular surface on which all physical observables remain finite. The curvature and matter density diverge in the classical theory, but they have their maximum universal values in the in loop quantum gravity, and this is the maximum of the density goes like 1 upon a delta cube. As in the classical limit, delta, the area gap of course goes to 0, and therefore that blows up. The curvature radius, not curvature, curvature blows up classically. So curvature radius classically goes to 0, but quantum mechanically curvature does not blow up, and curvature radius is a minimum, which is about 1.2 Planck length. I'm giving you a little bit detail so that you can compare with what happens in Schwarzschild. So in LQC, you can actually take the wave function in the full and have a Hamiltonian constraint, and you can actually evolve it, or you can look at so the peak of this wave function, and you can plot the peak of the wave function, and you can see the following, that this is the volume of the fiducial cell, and this is the scalar field, and you are using scalar field, if you like, as time. And what you find is that, or you're using volume as either of them could be used as the time up here. So in the classical theory, this actually is decreasing all along, and will actually, the volume will go to 0, and that is a Big Bang singularity. But in quantum mechanically, as you have seen before, probably, that you have got a big bounce, and the singularity is actually resolved. And the statement is that instead of using this wave function, we can reproduce this dynamical trajectory, which is followed by the peak of the wave function, using the so-called effective equations. And these effective equations is really that the classical equations are in green, and the quantum correction is red. And this rho sup came from this curvature that I just mentioned, which is about 0.41 millimeter. And the matter density operator has actually an upper bound explicitly. And this provides a precise sense in which the singularity is resolved. So to summarize, we had a lot of experience in loop quantum cosmology, and in loop quantum cosmology, we know that singularity is resolved, and the physical observables all remain finite. There is no problem. Now we want to go to the Kruskal spacetime, and this is just a Kruskal spacetime. This is not there is no Hawking effect, just Schwarzschild by itself. And here, again, this interior is spatially homogeneous, and therefore we can use methods of loop quantum cosmology. And the ideas are very similar in that case. Okay, so what happens here? Situation is much more technically complicated than in the Friedman models up here, or even the Bianchi models that are extensively studied. And therefore, although the quantum Hamiltonian constraint has been written down explicitly, it has not been manipulated enough or solved enough to really see, to get a picture like that. So that's an open problem. That is something that could be handled with people who have enough computer skills. You could probably solve this problem up here. Oops, again. I don't know what is why. The second half suddenly I'm having these problems. Okay, I'll just leave it. So the situation is, yeah. So that's an open problem up here to solve with the wave function evolution. But the focus has been on effective equations, and that capture the key quantum corrections extremely well in the well-studied models, in the cosmological models. Even this analysis for the Schwarzschild or Kruskal picture is rather subtle. The analog of the mu naught and mu bar the analog of the mu naught and the mu bar schemes have been worked out, and the singularity has been resolved in both. However, the detailed examination revealed two important limitations. Namely, in the mu naught scheme, the physical results actually depend on infrared cutoff. So they depend on this L naught. This is not at all surprising, because the mu naught scheme had problems like that also in cosmology, in loop quantum cosmology. In both schemes, unfortunately, there are large quantum gravity effects in the low curvature region. So the low curvature region would be the one up here. There are large quantum gravity effects in the region like that. And the mu bar scheme, there is a further problem, namely that if in fact in both cases singularity is resolved. In the mu bar scheme, if I actually go across the singularity, which is resolved, then actually the two spheres that I got, they actually acquire radii which are smaller than the Planck, the area gap, and so therefore the mu bar scheme contradicts its own assumptions, so it's not self-consistent. So in loop quantum cosmology, we had these two schemes, mu naught, mu bar. Mu naught was ruled out, and mu bar stayed, and that is producing perfect results. This situation is more complicated, and in this case, neither of these schemes were free from limitations, particularly the physical limitations up here. So now the two schemes, oh God, this is really bad because everything is moved a little bit. Let me see if I can. The two schemes are distinguished by the way that the quantum parameters. So just like what we have here, mu bar here was a quantum parameter that came up. When you can converted C to the sign up here, this kind of a thing, and therefore there is a quantum parameter, and that is the effective equations always are these quantum parameters, and the quantum parameters here was mu bar and mu naught, but neither of them are good, and in the classical picture now we have got B and C, and therefore there are two such parameters up here, and the phase space functions. But one can select these quantum parameters differently. We cannot use the mu bar scheme or the mu naught scheme, but we can select them differently. And the idea here is to make them phase space functions, but which are constant along the effective trajectories, that is to say along Dirac observables. Then all those limitations are overcome, and the geometry of the quantum corrected spacetime has been worked out in detail. The singularity is replaced by three manifold. This is a three manifold that I am referring to, this three manifold. And this three manifold is called a transition surface, as I mentioned. To the past of it, I got trapped region, and to the future of it, I got untrapped region up here. Now, but there's some interesting things that happen, namely, let me see if I can do it quickly, if I cannot. I hope I just don't mess it up completely. Oh, good. Okay. So what happens is that you have got universal upper bounds on the let me just leave it like that and point out to the screen. Okay. So what I got is a universal upper bounds on the curvature scalars, and they are reached at this tau, the transition surface up here, and R squared goes like area, some numerical coefficient divided by area gap to square. Again, this is the Ricci tensor squared, that again goes like area gap squared, and Wild tensor also area gap squared. The numerical coefficients here are the same. Here it is different, but that's not surprising because we're looking at quite different objects up here. Is the Ricci part, and here is a Wild part up here. And there are subleading corrections, and they have all the same form. And the curvature radius, the minimum, the maximum curvature gives us a minimum curvature radius, and it is about 0.57 times LP, which is one half times the Friedman model. I'm just pointing out that you don't get ridiculously different results. You get results which are completely plausible, and there is no problem. And then as one moves away from this transition surface, curvature rapidly approaches the classical values, even when for the masses of the initial ADA masses of a black hole as small as 10 to the 4 Planck mass. The radiative correction in this case is about 10 to the relative radiation correction. The relative quantum correction in this case is about 10 to the minus 15, and for a solar mass black hole it is about 10 to the minus 150. So even though the bounce is not exactly symmetric, the radii of the trapping and anti-trapping horizons are almost the same. 3 kilometers, then if the trapping radius is 3 kilometers, then the anti-trapping radius is about 3 plus 10 to the minus 25 times 3 kilometers, as one would expect, since there is no physical mechanism for macroscopic mass inflation or deflation. Surprisingly, this is quite non-trivial to achieve. So the point is that you have got these schemes which are meant to capture the leading order quantum corrections. We have these effective equations up here. And the only point I'm communicating is that it turned out to be extremely difficult. It took almost 10 years to understand exactly what is happening. It turns out extremely difficult. The naive generalizations of the loop quantum cosmology model did not work. One really had to introduce new ideas and do very careful analytical as well as mathematical as well as numerical simulations to see really what is happening up here. And what is happening is that, in fact, singularity is resolved. The You got this the transition surface and the transition surface as universal properties. The important thing up here is that this curvature upper bounds are universal. They don't depend on the mass of the black hole. The mass of the black hole only comes in the subleading term. The leading terms are independent of the mass of the black hole. And this is really important, as we're going to see. As we're going to see in detail up here. And the second thing is that in this other schemes that I talked about, mu naught and mu bar scheme up here that I talked about up here, when you are close to the horizon, these corrections that I am talking about were actually quite large, whereas this correction that I have mentioned up here is large. But there is a consistent scheme, and one can achieve that, but it requires rather careful analysis. And there is one kind of very important, for me conceptually, this was for me the icing on the cake that really clinched that this was a reasonable scheme to use. Namely, there is a contradiction. You see, because we got d by dx as a Killing vector field, therefore, what we have is really a notion of a Komar mass. So this geometry has a Komar mass, a constant mass up here. So I got a Komar mass here, a Komar mass here. Now in classical general relativity, I got Ritchie scalar Ritchie tensor is identically 0, it's a vacuum solution, and therefore the Komar mass on two sphere is the same as the Komar mass on the other two sphere, because you can check that just because of identities of differential geometrical identities, that if I got two spheres, then the difference between the Komar mass is given by the Ritchie tensor, and I've just written down the Ritchie tensor as the effective stationary tensor minus effective minus half the trace of the effect of the stationary tensor. So what do I mean by this? As we saw up here already, the Ritchie tensor is not 0. The quantum, and it's all correction, it's all depends on it. The classical immediate goes to 0 because this goes to 0 up here, but Ritchie tensor is not really 0 up here. A classical limit, the Ritchie tensor, the classical limit Ritchie tensor goes to 0. I'm not explaining it very well. Classical tensor, there is no problem. But here there really is a quantum mechanical object up here, because this I am looking at the Ritchie tensor very close to the what was the classical singularity. Therefore I got this formula up here. Classically the Ritchie tensor is 0, but quantum mechanically is not 0, and therefore there is an effective stress-energy tensor. And the effective stress-energy tensor is of certain form, and the difference between the Komar mass is given by the integral of the effective stress-energy tensor on this tube that I got. And now the point is that near the surface up here, the effective stress-energy tensor is actually very large. Okay? This effect. So this is very large. And therefore, you would think that this mass is very different from this mass, and therefore, the mass on the anti-trapping horizon will be quite different from the mass at the trapping horizon. These two things will be quite different. And indeed, this is quite macroscopic. For a macroscopic black hole, this is really macroscopic up here. But it turns out that when you look at the details, this integral turns out to be precisely minus the mass of the trapping horizon, and therefore, this equation just says that the mass of the anti-trapping horizon is just minus the mass of the trapping horizon. And the mass of the trapping horizon, and that is completely correct, because here the Killing vector field is future directed, and here the Killing vector field is past directed. And therefore, this is completely correct. And so that resolves a potential problem that you might have thought, namely, wait a minute, there is something funny here. How can the mass here be equal to the mass here? And the statement is that the two things are true. And this was not always the case with many regularization schemes that had been actually looked at. Okay, and this brings us to the last part, which is the singularity resolution in the quantum extension of the semi-classical approximation. So here what I did was to look at what Carlo was saying, like was non-dissipative part, namely I just look at the singularity in the classical picture. Now we also have to consider the Hawking radiation and see what happens up here. So in this case, the statement is that I got this, the picture I got is the one that I've written up here. The semi-classical region is in yellow. I got this dynamical horizon forming up here and then it is disappearing. This is the CGHS model. and the singularity already in the classical region is C0 but not C1 by quantum corrections. LQG provides strong evidence that the metric would be a well-defined operator value distribution in the full quantum theory as well, and two rather tame assumptions in the CGHS model lead to a conclusion that in fact this chi plus is infinitely long, and in fact the state on this chi plus in CGHS model is exactly is a pure state, and there are correlations between late times and early times. So this is what I would like to explain. So this is a CGHS model, and we are going beyond the semi-classical approximation. Here I send an incoming vacuum state. Over here I will get I mean, since this is a scalar field, the scalar field just propagates, and I get the vacuum state on all of them. Now in the Hawking radiation case, it became a mixed state because we had to trace over here. Therefore, in the full quantum gravity model, if in fact this length, this affine parameter was not the scry of the physical space-time, where the question is what is the range of the affine parameter. If this affine parameter was not equal to, not infinite, then the statement would have been that this scry would not be, so to say, as long, as complete as this scry up here, and therefore the state that came up here would not be a pure state in a Fock space at plus infinity. So let me state again, we know what the state up here is. The question is, what is its interpretation with respect to the physical metric GAB? That is the question, physical metric. So is this scry long enough in the physical metric? The answer turns out to be yes, under these two assumptions, which I will say in a minute what they are. The assumption is yes. And the second question we want to ask is that I got this state up here, which was just evolved trivially in Minkowski space, but I am interpreting this state in the physical space-time, and in the physical space-time, is that state in the future Fock space of G hat AB at scry plus, and if it is in the future Fock space of G hat AB, then what is happening? Are there correlations between late times and early times? These are the questions we want to ask, and the answer to all the three questions are yes, if you make these two assumptions. The first assumption is that the metric, which we expect it to be operator value distribution, but we have not worked it out because the equations are complicated. If we assume that this metric, this operator value distribution, I take its expectation value in this state, a Heisenberg state we have got, it's all in the Heisenberg picture, and the question is whether this metric then, I look at it all over the place up here, and in particular I look at in the neighborhood of scry plus. In the neighborhood of scry plus, the question is this metric, first of all, is there a scry plus for this metric, is it asymptotically flat, and the assumption is that yes, that it admits this scry plus, and the mean field approximation is very well here. So the idea here is that in this region I can really ignore the quantum fluctuations of geometry in the asymptotic flatness up here, and only look at the quantum fluctuations of matter, and the flux of quantum radiation ends at some finite time. Now, this can be weakened to say that the flux that actually it ends at much later time. Under these two assumptions, it turns out that the answers to all these questions are yes, namely that I got a vacuum state up here, which is trivially evolved to a certain state up here. The interpretation of that state in the physical geometry of this expectation value of G hat is indeed such that the space-time is actually, scry of this space-time is actually complete. And the statement is that, so there is no event horizon up here, and that the Heisenberg quantum state back minus is actually pure state in the future Fock space of at scry plus with respect to the physical metric, and it has an interpretation of being populated by pairs of correlated quanta, correlation between what happened at early time when the quanta were emitted, quanta emission starts here early time, and then I got late times up here. So even for this model there is scope for further work, this is for students, and results could be made sharper using techniques introduced by Deutsch and Fredenhagen in rigorous quantum field theory. So, those of you who are interested in quantum field theory might want to do that. And also further detailed calculations will provide valuable insights on the purification process. Yeah, I mean, I can explain that to those who are interested in detail what one could do. But already it bears out the loop quantum gravity paradigm. And now for the more realistic collapse model, here was a semi-classical picture that was Hawking had proposed with a future singularity, and it is now replaced by this picture up here. In both these cases, the semi-classical region is in yellow, and what I am doing up here is an extension of the semi-classical region. And the extension of the semi-classical region is that, as we saw in CGHS model, there is nothing funny along the last ray, so we hope that the metric can be continued here. But even in the semi-classical region, there is some conceptual differences between these two things. Namely, in LQG, what forms and evaporates, as we saw up here, is a dynamical horizon, and there is no event horizon. In LQG, there is no singularity, and LQG analysis of the crustal interior suggests the singularity is replaced by a transition surface up here, to the past of which we have got a trapped region, and to the future of which we have got an anti-trapped region. And there is no event horizon and there is no singularity. In both cases, the curvature reaches the Planck scale in both cases, when the curvature reaches Planck scale, the semi-classical analysis cannot be trusted. In the Hawking picture, singularity is just maintained to the future boundary. The fact that curvature attains the Planck scale near it is actually ignored. So, why should we trust classical general relativity? In loop quantum gravity, what we have is this pink region where quantum gravity effects are going to be important. This pink region is the one which is surrounding the transition surface. And in this pink region, there are two independent quantum gravity effects. So, this is what I would like to understand. I would like you to understand, especially those who are following this thing in some detail. So, in this pink region, this is the region in which is sort of semi-classical region is completely valid to the below this pink region, to the south of this pink region, if you like. But at the pink region itself, we have to consider the quantum gravity effect, because after all, that is where the singularity was resolved. And there are two different things here. The first is that there is a negative energy falling by the Hawking quanta. All along here, there is a negative energy that is entangled with what is happening outside, namely the quanta which went out to infinity are entangled with quanta which fell in. Now, this effect is completely negligible at the left end, because here the black hole is macroscopic, and it's evaporating extremely slowly, but it becomes more and more important as you move to the right hand side. And it grows, this Hawking radiation grows very, very slowly, but it becomes very important at this blob, the right blob, that is the end of this transition surface that I have talked about, that I have mentioned up here. And but there is a second effect, and the second effect is something that is not often considered, and that came from what happened in the Kruskal space-time. Remember, in the Kruskal space-time, we got a transition effect, transition surface up here, and on the transition surface, we looked at the effective stress energy tensor, which is really given by the Ricci tensor up here. We looked at that effective stress energy tensor up here, and that effective stress energy tensor was large and negative, and that is important, right? Classically, there is no stress energy tensor. It's a quantum-induced stress energy tensor. The loop quantum gravity effects induce stress energy tensor. In other words, in the interior, what we have is the loop quantum gravity effective equations, which include quantum corrections to the classical equations. Classically, Ricci tensor is completely 0. Quantum mechanically, Ricci tensor is very close to 0, almost 0, near the horizon, like 10 to the minus 150 factor near the horizon. But as we come to near the singularity, the Ricci tensor grows, and near the transition surface, which replaces the singularity, the Ricci tensor is quite large. And because the rigid tensor is quite large, the stress strain tensor is also quite large up here. And therefore, I got negative energy coming up here. And furthermore, I emphasize purposely the fact that these stress strain tensor that I am talking about, this effective one that I am talking about, that does not depend on the mass of the black hole. That is universal. If it is universal, then the second effect is actually constant all along here. So there is a negative stress strain tensor coming from the second effect all along here. And we have to better understand the relation between the two effects up here better. But the first effect already says that even though there was a macroscopic energy, solar mass energy that fell in, the quantum effects up here with the negative energy, the total energy up here is very small. So what Carlo was talking about, what is bouncing and so on from here, whatever is happening there, it's extremely small energy that is going to happen up here. So that is the important part up here. Throughout the pink region, except at the right block up here, both effects can be analyzed using what is known as the effective dressed metric. It's a smooth metric whose coefficients, however, depend on h bar, thereby incorporating the leading quantum corrections. Therefore, I believe that this phase can be analyzed regarding the Hawking partner modes as quantum fields propagating on this dress effective metric. So, I got these modes that are coming in here, and the statement is that almost everywhere here this can be analyzed using a dressed effective metric that is available, for example, for considerations of loop quantum cosmology. We can construct the same thing here. This analysis is an important open problem, and I think that this can be done, and this is something that I would like to suggest to students that they might want to look at it. It is feasible and will reveal interesting physics. Once we are on the other side of the pink region, there is an anti-trapping horizon, and on the future of the anti-trapping horizon, the curvature diminishes extremely rapidly in a few Planck lengths. The curvature here becomes very zero, very small, and therefore this evolution will be much more easy, quite easy up here. And the late time modes will be correlated with the early time Hawking radiation. So basically, we had this mode that came out, which fell in, and these modes then come up, and these modes will be correlated with what happened at early time up here. And that will restore purity. Just as so this is very similar to what was mentioned before about Page's charcoal example. Supposing I got a charcoal and I light it. So I thought there was a slight difference with what Carlo was saying, but maybe I misunderstood. Supposing I have this charcoal and I light it. Then immediately after it is lit, it emits photons, and therefore the quantum state of the charcoal is really correlated with these photons. Then the temperature decreases, the photon becomes longer and longer wavelength, takes a long time, and then finally, hopefully the charcoal just goes to its ground state if it was an ideal situation, if it done in a zero temperature experiment, a thought experiment up here. And then it looks like I only have these photons, and these photons look like a mixed state. And so what is happening up here? What is happening is that these extremely long wavelength modes that are coming out at late times are correlated with the short wavelength modes that came out at early times, and that is why the total state is a pure state, just as the initial state was a pure state up here. And the claim is that the same thing is happening up here. But what is, to me, sort of fascinating and open, and I've been sort of thinking about it for a long time now, is really this red blob. What is this red blob? It is the right end of this pink region, which is really the Planck region surrounding the region in which the curvature is Planck scale surrounding the transition surface up here. Now, why is the right-hand side so important, or why is it more complicated? Well, because we cannot use these effective equations that I have talked about before, and the reason is because we cannot make adiabatic approximation. As we are approaching this region up here, the black hole is shrinking and it evaporates faster and faster, quicker and quicker, and therefore towards the end adiabatic approximation is no longer valued, and I cannot use my dressed effective metric up here, and I really need to know what is happening up here, and what is happening up here could actually in principle affect what is happening everywhere here. And we have to sort of make sure that that doesn't happen, that what really happens is really whatever is happening up here only affects the part of scribe which is null related to this. And furthermore, there is something more important, namely that as I am approaching this red region, black hole is shrinking, and therefore the modes which are emitted here are more and more ultraviolet. What comes out of here is going to be infrared. So this red region holds the key to understanding how this transition from the ultraviolet radiation of very, very high frequency to very, very low frequency occurs. Fortunately, the CGHS provides us some hints, and we can actually use them. Okay. Let me just sort of, there are a couple of remarks I wanted to make, maybe I don't have, and then I'm about to end. So again, this is my first slide. This was my hope and aim, and I hope I achieved at least some of it. So there are a couple of remarks I wanted to make. That, namely, that this might all seem reasonable to many people here, because you already know about loop quantum cosmology, you know singularity resolution, you have these ideas, relativity ideas rather than particle physics ideas. But it's not something that is universally accepted at all. There are a lot of people who string theory people. I mean, my close friend Gary Horowitz, for example, has written a paper with Engelhardt saying that even in the quantum theory suggested by string theory, singularities will persist. Similarly, my other close friends, Bob Bald and Bill Unruh, think again that the singularity will actually persist. You know, there's no problem, there will not be any problem up here. So I don't believe that that is correct. They are correct, because I think there are no singularities in the real world. They will not persist. But I just want you to know this. The second thing is that there is a lot of claims about astrophysics. I mentioned to you agree already. Namely, you know, for example, that there may be effects, quantum effects of gravity that one might be able to see in using gravitational waves, LIGO, etc. And I don't think that is correct either. And the reason why it's not correct is because, as we saw, near the horizon for astrophysical black holes, the quantum geometry effects are very, very small, are completely negligible, 10 to the minus 115. And so LIGO is not going to be able to see it. It's not that they're not there. It's just like this chair is quantum mechanical. But it will be very difficult for me to put it in a superposition state and see some quantum effects. So that is happening. And also, I think that there is a lot of work on potentially astrophysical and cosmological signatures, either primordial black holes or fast radio bursts, et cetera, et cetera. I want to encourage very much people to think about it. But for young people, you should also be aware that these are fascinating ideas, but their lifetime has tended to be quite small. In other words, one tries something, and then finally observations rule it out. For example, this idea that came not from loop quantum gravity, but other circles, that semi-classical gravity must fail at the horizon because of firewalls. It was taken very seriously by many, many people. That idea is essentially failed now. Now you don't hear it. Why? Because the LIGO observation has shown that there is nothing profound that happens near the horizon. There is no firewall there at all. There is nothing there at all. So I just wanted to mention that, and then I'll stop. Thank you.
Once again, we might have time for one question. If there are none, then, okay, one question.
So I have a very small question. So consider this loop quantum effect in this dilaton model, this two-dimensional model.
I can't hear very well because I
So I mean, from loop quantum black hole, we know is like this transition surface is contained in this black hole horizon and the white hole horizon. So could it happen like in this CGHS model? So this square plus in the future becomes a white hole horizon.
No, CGHS model square plus is not CGHS model, it is not true that square plus becomes a horizon. CGHS model, maybe we can talk.
I mean, in this model, you see like if there is this singularity resolution,
yeah.
so the space-time will be complete, and there will be this square plus there.
Yeah.
Yes. And what will happen if after the last ray, so this is actually a white hole horizon rather than a square plus?
No, the white hole horizon is right here. So in this case, First of all, I don't like the term white hole, as Carlo knows very well. White hole, black hole, it gives a wrong connotation to the outside world because white holes have singularities generally, and they have a connotation that anything can come out of white holes. There is no predictability associated with that. That's true of the white holes. But what we are talking about, we have predictability. So this is not really a white hole. So I got anti-trapping region up here, and there will be an anti-trapping. So these are supposed to be the tame singularity in the semi-classical picture. In the quantum picture, this will not be here at all. They'll be replaced really by transition surface and the horizon, and the anti-trapping horizon is somewhere here, right? And then these modes will come out. Anti-trapping horizon is here, and the modes will come out. Okay. So it's very similar to here. Namely, I got anti-trapping horizon here, and the mode cell can come out.
Okay. Thank you.
It's very similar to that, yeah. So it's not true that. So you're thinking of that maybe scry is like the white hole or something. No. The anti-trapping horizon. This is not trapped, or this is not trapped or anti-trapped. This is this normal region, and then I got here.
Okay, let us thank our speaker again.